Hello everyone, in this video we're going to be differentiating the homotopic, enantiotopic, and diastereotopic protons. They are very important to be able to identify in the proton NMR. So let's jump into the homotopic proton. So whenever you have a presence of the axis of an symmetry, then you're going to have a homotopic proton. So now that may kind of confuse you what's axis of symmetry and whatnot. So there is actually an easier way to figure out if a given proton is indeed going to be in a homotopic or not. So let's talk about the axis of symmetry momentarily. If I rotate this first molecule that I have driven out here, so do a rotation by 180 degrees, what's really going to be seeing on the other side? And I'm really going to be focusing on the protons that are in the middle carbon here. So I'm going to call this 1 and I'm going to call this 1 prime. And when I rotate this, and I'm just going to copy this down here, then you exactly gonna see something like this. And when you suppose you have your eyes closed, and as soon as you rotated it, and when you see it on the other side after opening your eyes, you can't really tell the difference between those two protons. You don't know which one is the 1 and which one is the 1 prime because your sides are going to be the same. So the sides you have here and here, the sides here and here, they're actually the same. So there's really not any difference between those two protons. So this could be either 1 and 1 prime, or it could be the other way, where it could be this first one could have been the 1 prime and this could have been the 1. So I'm just going to be saying it only one way. So there is really not any difference, but I can see this could be very confusing for students to understand. So there is actually an easier way to figure out if a given proton is going to be homotopic or not. So I'm going to be taking the same example and we're running in a replacement test. So when we say in a replacement test, what we're going to be doing, we're going to be drawing two molecules again, and in those we're going to be replacing those hydrogens with the deuterium one by one. Now, why would I pick deuterium? Well, it's just easier. You don't necessarily have to pick deuterium. You could pick something else as well, as long as it's not the hydrogen. So when I do replace, suppose this one with a deuterium, I'll have deuterium here, and in the second case, I will replace the other hydrogen with the deuterium. Now, do I see any difference between those two structures that we have drawn here? Well, no, both of these are actually going to be the same. So when they give you the same molecule, even after drawing, even after replacing one of the hydrogens with the deuterium one by one, you're going to be running into an homotopic protons. So your homotopic protons are actually equivalent. You're not going to be seeing two different signals in the NMR. It's just going to be one signal for those two protons in the NMR. Let's take a couple of more examples here. I got this cyclohexane here, and in cyclohexane, if I draw this proton here and I'll draw another one here, so I can draw one with the solid wedge and the other one with the dash actually. So I can run a replacement test again on it. So when I run a replacement test on it, so let me just copy this down here. In one case, I would replace this by D, and in the other case, I would replace the other hydrogen with D. So there's really not any difference between those two. So as a result, they are going to be the same, they are going to be identical, so that makes those are your homotopic protons. And in a given homotopic proton, you don't really have a prochiral center. So we'll talk about the prochiral center when we talk about enantiotopic protons, but if you don't see any prochiral center, that means those protons are going to be homotopic. In addition, if you have a methyl group or CH3 group, those three protons are always going to be homotopic, because even if you replace one with the D or some other element, the other two still stays the same. They're not becoming chiral at all. So CH3 is always going to be homotopic. The question is always going to be when you have a CH2 or in a methylene group. So in that case, whether those two protons are going to be homotopic or enantiotopic or something else, that's the thing you have to kind of look into. Now let's look at this next example. Again, doing a replacement test. So let me just Maybe make a space a little bit down there. So when I do a replacement test, I'll draw one of them here and the other one right here. So what I'm really doing here, I'm going to be replacing those with the deuterium 1y1. So what I'm going to do, I'm going to take the top hydrogen, replace it with the deuterium, bottom one with the deuterium. Now figure out if there is any difference between those two structures. Now I know my deuterium is on the top in the first structure and I can't really rotate it because the rotation around the double bond is restricted. However, there's really not any difference because this environment, the deuterium and this metal, and then you have in the second case the hydrogen with this metal here, and then you can say the same thing about your second compound where you have the hydrogen with the metal group and then you got the deuterium with the metal group. So there's really not any difference in the environment surrounding your deuterium and the hydrogen, and since there's no difference, those are still going to be your homotopic protons. If you had, like suppose if you had a metal group, so I can say at this particular position, if you had, instead of in a metal group, you had a hydrogen here or something else, or maybe a bigger group, that's when those two protons would not been the homotopic, but rather they would have been the diastereotopic. So we'll take that example in a little bit, but those two are going to be your homotopic protons. Let's talk about enantiotopic protons. So in an enantiotopic protons, you're going to have a plane of symmetry. Instead of axis of symmetry, you're going to have a plane of symmetry. So what that really means, if I rotate this molecule that I have here by 180 degrees, what I'm going to get on the other side, you're going to have NH2 on this side and you're going to have CH3 on this side, and then you're going to have this hydrogen here, and then you're going to have this other hydrogen here. So you can't really interconvert those two particular hydrogens in the middle carbon when you have this, when you rotate it by 180 degree. Now I understand this could be hard when you kind of rotating it, and how would you know whether it's going to be an enantiotopic or not an enantiotopic. So the easier way to figure that, it's going to have a prochiral center. What that means, if you replace one of those hydrogens with something else, all of a sudden that particular carbon is going to be chiral. So right now, this particular carbon right there is going to be prochiral because we have two hydrogens on it. But if I replace one of this hydrogen with something else, this is going to become chiral. So that's when you're going to have those enantiotopic protons. Well, we can still do the replacement test. So let's try to run a replacement test on it. So let me just gonna copy that, copy another one here. So I got two of those there. So now what I'm gonna do, I'm gonna replace those hydrogens with the deuterium or some other element. Doesn't necessarily have to be deuterium, but deuterium is commonly used when you do the replacement test. Now all of a sudden what happens? All of a sudden this carbon right there becomes chiral, because now it has four different groups attached to it. We got hydrogen, we got deuterium, we have a methyl on the left side, and we got an NH2 on the right side. So all those four atoms or group of atoms are different. The same story on the bottom here. We got deuterium, hydrogen, we got the methyl group on the left side, and we got the NH2. Now, what's going to be the relation between those two? Well, if you look here, the only thing that's going to be different among those two is the position of the hydrogen and the deuterium. And if I want to go ahead and figure out what the R and the S center is going to be, I know this NH2 is going to be 1 here, this CH3 is going to be 2 here, deuterium is going to be 3, and your hydrogen is going to be 4. So you can clearly see it's going clockwise when you're going from 1 to 2 to 3. But remember, your deuterium is going back into the page, so you have to flip it. So when you flip it, it's going to be going counterclockwise. So this particular one is S. And when you do the second one, we're going to have 1 here, 2 here, 3 here, and 4 here. So in this particular case, you don't really have to flip anything because your lowest priority group is already back in the page. So when you follow 1 to 2 to 3 in the form of a circle, it's actually going to be going clockwise, so that's going to be an R. So one of them is an S and the other one is an R. So what that means, they are going to be the enantiomers of one another. And that's why those two protons that we have earlier, that's going to be, let's call this 1 and 2, those two protons have a relationship of enantiotopic protons with one another. How do they show up on the NMR? Mostly your enantiotopic protons are going to be equivalent in the NMR spectrum, and they will have the same chemical shift, except if you're using a chiral solvent. Well, for the most part, you're going to be using a chloroform D or a methanol D, and those are not chiral solvents. So you're going to be seeing those enantiotopic protons to be equivalent. Anytime if you use chiral solvents, that's when they're going to be not equivalent and they're going to have different chemical shifts. Let's look at this next one here. Well, we have which particular protons you're going to be focusing on here. Well, remember your CH3s are always going to be equivalent. If you have a CH3 proton or a metal protons, they're always going to be equivalent. So what I'm really focusing on here, I'm going to be focusing on these two protons here. One of them is right there and the other one is right there. And then that particular center is actually going to be a prochiral center because right now it's got two hydrogens. We got a methyl group on the right side and this carbonyl R group on the left side. So that is indeed in a prochiral center. But to double check, do a replacement test. So when I run a replacement test, let me just copy that down here, actually twice. I'm going to be replacing this hydrogen with the deuterium, and then, oops, I'm going to be replacing this hydrogen with the deuterium. So all of a sudden what happens, these two molecules or two structures that I have drawn here, those are going to be the enantiomers of one another. So since they are the enantiomers of one another, these two protons originally they're going to be the enantiotopic protons. So always keep in mind in an enantiotopic protons you're going to have a prochiral center. Let's look at another example here. Well, the only thing I'm going to be looking here, two protons right there. So those two protons are going to be, if I replace it with the deuterium, then that particular carbon is going to become a chiral center, and having the deuterium into the page and out of the page will make a difference in terms of the chirality. So as a result, those two protons are going to be your enantiotopic protons. Do you have any other proton here that could be counted as an enantiotopic proton? Well, the answer is yes. If you look at these protons right there, those are also going to be your enantiotopic protons because it does have an prochiral center, and when I do replace, they do have an prochiral center, and when I do replace those hydrogens with the deuterium one by one, you're going to be getting the enantiomers. So since you're going to be getting the enantiomers, those two are also going to be your enantiotopic protons. Look at this diastereotopic protons. Now in diastereotopic protons, you already going to have a prochiral center, but there is going to be an existing stereo center. So that's the difference between the enantiotopic protons and the diastereotopic protons. And they are not going to be equivalent, all right? They will have a different chemical shift. Now, there are going to be times when the two diastereotopic protons just happen to be having the same chemical shift, and that really depends on how far away they are from the chiral center. But further away they are from the chiral center, more likely that their chemical shift is going to be very close to one another. But if they are closer to the chiral center, then their chemical shift is going to be further away. So now if I look at, suppose this particular proton here, one coming out of the page here, and then the other one going back into the page, and obviously we're not really focusing on the CH3s because your CH3s are always going to be homotopic. So when I go ahead and run a replacement test here, what's going to happen? I'll replace each one of those with the deuterium one by one. So let me just copy this down here, and copy this down here. And now I replace this with the deuterium. and then I replace this particular one with deuterium as well. Now what happens? This particular chiral center all of a sudden is flipped. However, the other chiral center that we got in there, which is going to be this guy right there, that chiral center is still staying the same. So anytime you have two chiral centers and you're comparing the two structures with one another, and if they are not the mirror images of one another, then they are going to be the diastereomers. And since they are the diastereomers, the protons that we have mentioned earlier, so I can call this proton 1 and proton 2, those two protons are going to be your diastereotopic protons, and they will be showing at different chemical shifts on the proton NMR. They're not going to be equivalent. So the bottom line here was this would be considered as an aprochiral center, and you already have an existing chiral center in there. We already have this carbon with the chlorine metal group attached onto the right side. That's already in a chiral center there. What about this next one here? Let's look at here how many diastereotopic protons we got here. Let's focus on this proton right there and that proton right there. So those two are going to be diastereotopic because remember, if I go ahead and draw out the replacement test on those and replace this one with the D and then replace this one with the D. Now all of a sudden those that become the chiral center. So this is going to be your chiral center right there. So since this is the chiral center, you're going to have a flipped configuration there. And since it's in a flipped configuration, the other chiral center that you have in the molecule that's already present, which is this guy right there, the configuration of that one is not really changing. So as a result, the relation between those two is going to be they are diastereomers. So since they are the diastereomers, those two protons that we have mentioned before, they are going to be diastereotopic protons, and they're going to be showing at different locations, or they're going to have a different chemical shifts. Do you see any other diastereotopic protons in there? Well, if you can focus, if you can figure out that this particular one right there and this particular one right there, those two protons are also going to be the diastereotopic. I do have another example here. Let me just copy this down a little bit. And if I do a replacement test on this, so one of them is right there and the other one is right there. It's running out of space there. So in one case, I'm going to be replacing this with the deuterium, and in the second case, I'm going to be replacing the hydrogen that's on the right side, that's on the left side with the deuterium. So now what's going to be the relation between those two? The relation between those two, you have one of the chiral centers still staying the same. So this one and this one is still the same, and then the other chiral center is flipped. This chiral center and that chiral center is flipped now. So as a result, they are going to be the diastereomers with one another. And since they are diastereomers, these two protons right there are going to be your diastereotopic protons, and they will have a different chemical shift. Before we go, I do want to mention one more example that's going to be similar to what we have seen in the homotopic protons. Let's suppose I got a double bond right there, and I'm looking at these protons here. I got H1, call this H2. Someone might think that those two protons are actually going to be the same, but they are not really the same, but rather they're going to be the diastereotopic protons. And why is that? Let's run a replacement test. So if I replace this with the deuterium in the first case and replace this second one here on the second structure with the deuterium, now what really happens? What's going to be the relation between those two? We can clearly see in case of the top structure, the deuterium is kind of close to the hydrogen here, And in the second structure, the hydrogen is close to the hydrogen that's going to be on the other carbon. So this particular one is going to be cis, and this particular one is going to be the trans. So they are going to be the diastereomers of one another. So remember, the geometric isomers is just another type of diastereomers. You're just not going to have only R and S having the diastereomers. You can also have cis-trans being your diastereomers. So those two protons are going to be your diastereotopic protons. Okay, so this is how you're going to be figuring out your homotopic, your enantiotopic, and your diastereotopic protons. So if you have any questions, feel free to leave any comments in the section below.